Yep, we're going to do this at some point. Okay, so the first thing I want to talk about, how many people are actually able to, even if you can get on the internet, access, like, how many people are like locked out of Canvas? How many people have trouble accessing the internet? And apparently some professor said, you're doing all your assignments, go to McDonald's, get Wi-Fi. I don't actually think we're allowed to do that. So I don't, I'm talking to administrators about this, but as of right now, until something like there's some kind of solid fix, we're going to continue to try to do the written assignments, but like I can't even print. So if you guys can't access the internet, we can't do quizzes. If I can't print, we can't do exams. So until things get fixed, what I'm going to do, since this makes me mad, and this is what I do when things make me mad, is I'm just going to put points in the Canvas so that we stay on track, because my mind will freak out if I don't have all the points in there. And so once things get fixed, we'll go back to the regular schedule. But until then, we're really just going to be doing the written assignments, because we can't, not everyone can do the rest of it. If anyone's super disappointed, yeah, keep it to yourself. So that's the only thing I can think to do. Because there's some people who were logged out of Canvas for long enough that they didn't get cached in the system. They can't even log in now. Nope, but you're getting points for it. I had a feeling you'd be fine with the arrangement. Okay. So I was disappointed because I make wonderful quizzes. So I'm super disappointed. But we will just do the best we can. Okay, so we're still working on gases, and this will catch up eventually. So we'll just do the best we can. So we have a mixture of 1 gram of H2 and 1 gram of helium. They're both placed in a 1 liter container at 27 Celsius. Calculate the partial pressure of each gas and the total pressure. Okay. Well, I already know one thing that I want to do. Can anyone, I mean, there's a number, so I just want to see if someone can get it. It's a pretty open-ended question. We will, but the first thing I want to do is I don't like Celsius in my calculations. So do what? Yep. So again, there are some of these gas problems that you could solve with Celsius and get the right answer, but it's not all of them. So it's best to just go ahead and take it to Kelvin and make sure that you're on the right temperature scale. Oh, that went up there pretty quick this time. Okay. Now, partial pressures. How do you think we're going to go about that? Um, we might be able to. Trying to think here. No, because we'd have to have multiple things changing if we use that. So what we can do, so first off, I use the ideal gas law. When you're at home, sometime try Dalton's law, see if it works, but I think too many things have to change to use it. So partial pressure, so that's the pressure of the H2 gas in the system, going to be the number of moles of H2, RT, oops, over V. Now, of course, we don't put a subscript on R because it's the same constant for all gases. Both gases are in the same container, so volume and temperature are going to be the same. We just need number of moles of H2. This will give us 0.495 moles of H2. Okay, now we can solve for the partial pressure of hydrogen. Let's see, 0.08206. And then the temperature. Over the 1 liter container. So hydrogen is going to donate 12.2 atmospheres to the container. So we have to do the same thing for helium. So again, partial pressure. Need the moles of helium. And now we can solve for the partial pressure. That will give us about 6.16 atmospheres. Okay, so then what did the rest of the question say? And so now we need the total pressure in the container. So this is where we use Dalton's law of partial pressure. So not a horrible problem. We're coming up next. You remember a term called mole fraction. We are just going to be playing catch up all semester. Okay, so it's going to have another Greek letter in it. So going to learn some more. Mhm. Okay, mole fraction. So the original way you look at it is, so that's a Greek letter chi. And so going to be we have a new where it's going to be the partial pressure of the gas you're looking at. I know it's unstable. So am I. Shut up. It always tells me your internet connection's unstable. Yeah, because I'm on a hot spot. So we have the partial pressure of the compound we're looking at divided by the total pressure in the system. So I wonder if we can construct a logical argument on how we get from here to here. So the way we construct mathematical arguments is every step has to follow from the one preceding it. And I say that, and that sounds like you're saying, well, yeah, no kidding. You would be surprised how many homework assignments I get where I'm like, the step you took from here to here, those two do not match each other. Happens a lot. That's when I write non sequitur on the assignment, and then they have to figure out what that means. So we switched from Greek to Latin. But okay. So first off, your first expression is dealing with mole numbers. How can I express mole numbers in terms of pressures? So let's just say the number of moles of compound one, that is going to be the partial pressure of compound one, V over RT. So now I can start putting those in. So if I look at my expression there, I can start saying, well, let's see, on the bottom, we're going to have P1 V over RT plus P2 V over RT. I'm looking at compound one. So I can just replace all the mole numbers with PV over RT. Then, you ever done the factoring out of a constant? So now, okay, so on the bottom, I'm going to have P1 plus P2 plus partial pressure 3, so on and so forth. P over RT. And P1 V over RT. This will give me P1 plus P2 plus P3, so on and so forth. And then what that ends up giving me so that's how we get from one to the other. You just use the ideal gas law. Yep, so V over RT is a constant. And so since they're the same constant, they will cancel each other out. Wait till we get to physics and we derive Coulomb's law by using Gauss's law. You're going to learn what a surface integral is. Just like this class, I can't make you use calculus in exams and homeworks, but we're going to look at it. Otherwise, with the textbooks, we have to make asinine assumptions to get from one point to another. And I'd rather just start with first principles and make the argument. It's like, well, why make assumptions we don't have to make when we could just do something that may push us outside of our comfort zone a little bit, but it actually shows us where things come from first principles. All righty. Now, the ones you're going to want to remember is either the mole fraction using the moles or mole fraction using pressure, because you're going to use these to solve problems. Well, to get there eventually, give it a second. All righty. Okay, 50-liter rigid container holds a certain mass of hydrogen gas and the same mass of helium gas. Total pressure in the container is 3 atmospheres at 25 Celsius. What is the partial pressure of hydrogen in the container? Now, I want you guys to take a few minutes and work on this, see if you can work backwards. This is a lot like the one we just did. It's just you're going the other way. The trick to this one is your value for N, your number of moles. What does that equal in terms of molar mass? Because like, for example, you could look up the molar mass of hydrogen and helium. So how could you change N into an expression involving molar mass? And when we're doing this, you guys can talk to each other. You can, you're one of those classes where you all hate each other. I can see it. I mean, I get why wrestlers don't talk. You all might have to beat each other up later. So that's called practice. Yeah, so you're right on top of the key there.
With that same amount.
So think of it this way, the units of molar mass are, so it's mass over moles. N is moles. So the molar mass, so the number of moles would be what over what? Over molar mass. So N is mass over molar mass. Everything has the same mass. So that's going to be able to cancel out of the mole fraction. So if you remember, your number of moles will be a mass over molar mass. And all the little n's are the same. So think about this. You can do something with that. So before when we were using like the subscript 1, this is what we meant. You're looking for the mole fraction of a specific compound. The 1 was just a stand-in for whatever molecule you're looking for. And then once you figure this out, remember your partial pressure you're going to use both of those. If someone gets there, your partial pressure of hydrogen should be 2 atmospheres. Just make sure you give yourselves, grace and leeway on this stuff. You've not been taught how to think about these problems at this level yet. So this is all like in brand new level. It's practice. Absolutely. Make it nice out of it. No, you're not going to set them equal to each other. The masses are equal. So all the little, right. So all the little n's are the same, and they'll all have different molar masses. And if you want to review it, this is problem number 100 from the back. It's from the end of the chapter. Just like with your written assignment, all of those problems are from the end of the chapter, and I made them odd numbers. So if you wanted to check yourself in the back of the book, you can do it. All right, let's start looking at this. So we want the whole thing we want is the partial pressure of H2. Okay. So the first thing I'm going to do is I'm going to remind myself that the partial pressure of H2 is going to equal the total pressure, which we have, multiplied by the mole fraction of H2. So if I find out the mole fraction of H2, I have the partial pressure. Okay, well, let's take this mole fraction in terms of our N numbers. And remember that N equals the mass over the divided by the molar mass. So that means, well, first let's space this out. So that's NH2 over, N total is NH2 plus moles of helium. Okay. So what this is going to end up being is so we're going to have mass over the molar mass of H2 plus the mass over the molar mass of helium. And on top, we're going to have mass over the molar mass of H2. Because the problem says all the masses are the same. Do you see a simplification I can make? Those all divide out. So this is going to give me 1 over, whoopsies, the molar mass of H2 over 1 over molar mass of H2 plus molar mass of helium. Now, if you're doing this on homework, this is as far as, I'm not going to make you simplify this any further. You're going to have to start combining fractions, and it's going to end up taking a while. Now, what is the molar mass of hydrogen? That's for one atom. What about H2? Yep. Over, we have 1 over 2.02 plus 1 over, you look at the periodic table, and helium is 4.0. Now we have numbers. So we'll use our calculator and figure that out, and we find out that the mole fraction of hydrogen is 0.66. Remember, your mole fractions are not going to have units. So think of them kind of like a percentage. This means that this gas mixture is pretty much 66% hydrogen. But now that I have that, I can go back to there. So the partial pressure of hydrogen is going to be my total pressure. I think this thing's going to blow up. Times the mole fraction I get 2 atmospheres. So remember, when you're solving problems, and this goes for chemistry and physics, when you're solving problems, don't start looking at the problem and saying and telling yourself, I don't know how to start until I can see the whole answer. That's going to make things that can make things turn out bad or make your homework take very, very long. There's always pieces you can answer. Treat them like puzzles. Find something you can solve that piece. Find something else you can solve that piece. Eventually, you put enough pieces in place, you go, oh, I can see it, hang on, and then you're able to put the whole thing together. Okay, collecting gas over water. You did a lab on this last semester, so I kind of wished we'd had this. So one of the things that so when you're collecting gas over water, the thing you're going to have to suss out, and the reason this is where Dalton's law comes in really handy, is if I'm doing a reaction, I get the gas from the reaction that bubbles through the water. What else do I get in the gas? So you do a reaction, it bubbles through the water, and above the water, I get a pocket of gas. It is a mixture of the gas you formed in the reaction plus water vapor. So we have to sort out the water gas from the reaction gas. So you can't always say whatever, like you're going to remember you get a certain volume of the water moved. That entire volume was not the gas from your reaction. Part of that was water vapor that was in there with that gas. So you have to start sorting those two out to get the actual solution to the problem. That was the best picture I could find. There's not much color to it, but you can kind of see the waters there, the hydrogen there. Hydrogen. Does anyone remember the technical term for this kind of molecule? Diatomic. What kind of diatomic? So carbon monoxide is one form of diatomic. Hydrogen is another form of diatomic. What would we call hydrogen? Homonuclear. Homonuclear diatomic. So that would make carbon monoxide a what? Heteronuclear diatomic. So we want to start make sure we're also practicing the jargon. Okay. So here we go. We have sodium chlorate decomposing to produce sodium chloride and oxygen gas. Let's see here. A 0.8765 gram sample of impure sodium chlorate was heated until the production of oxygen gas ceased. The oxygen gas collected over water occupied 57.2 milliliters at a temperature of 22 Celsius, pressure of 734 torr. Calculate the mass percent. Oh, there's a new one. The mass percent of sodium. What is that? NaClO3. Sodium chlorate. In the original sample, at 22C, the vapor pressure of water is 19.8 torr. So that's already giving you what? With the pressure, so the partial pressure of the water vapor. So those water vapor partial pressures are on tables. You can look those up. So you're just thinking about the temperature in the room, go, well, how much water vapor is going to be in that mixture up there? Well, you just find the partial pressure and you can figure that out. Now, NaClO3. Why did I name that sodium chlorate? What kind of compound is it? Covalent or ionic? It's ionic. Because if it wasn't ionic, at the very least, it'd have to have a trioxide in it somewhere. But it's ionic. So I don't know if you actually spent time, like if you worked on them last semester, but your ClO3, that is called an oxoanion. So it's a polyatomic ion, and there's a whole family of them. So if you know one of them, you know all of them. Can you tell me the charge on ClO3? -1, because it's paired with one sodium, which we know based off its position on the periodic table has to be a +1. I see some faces in the room that are like, what the heck? So we'll try to review these things as we go along. But so like your oxoanion families, all of them are going to differ from each other by one oxygen, and they all have the same charge. So like ClO3 is chlorate, ClO4 is perchlorate, both at a -1. ClO2 would be chlorite, and then ClO would be hypochlorite. So that's the structure of your oxoanion families, and they're all going to be a -1. So if you have something that's sodium chlorite, and you go, well, I didn't learn that polyatomic, well, but you know chlorate. So take an oxygen off the chlorate and you got the chloride. Okay, so the first thing I want you to do is write the chemical reaction equation. In that gram of the original sample of sodium chlorate was solid. Let's see if it says yep, it tells you. And so this is a decomposition reaction, so it has to have a very specific format that's going to be one reactant decays into multiple products. That's going to be the format for all your decompositions. So that one's a solid. On something like this, I would accept either solid or aqueous because we know that salt will dissolve in water to a certain point. What's the phase on the gas? Oh, well, that is, damn it. All right. Moving on. Then, can anyone see the stoichiometric balance? 223. So that is your reaction equation. Now, the key to solving this is we need to know moles of O2 in the product to find moles of sodium chlorate. So, above the water, we have these partial pressures. This was part of the key to reactions done over water. You're going to have the partial pressures of each gas. Now, the partial pressure of O2 is going to be the total pressure minus the partial pressure of water, which is going to be 734 torr minus 19.8 torr. So now we have our partial pressure of oxygen in that system. Okay. Now, how do we find moles of oxygen? So now we're going to take our moles of O2, going to be the partial pressure of O2, V over RT. Okay, so a couple of things I want to do here. Uh-oh. So our temperature is 295 Kelvin. What else do I want to do? Atmospheres. Let's see, one atmosphere. 760 torr. 0.940 atmospheres. Now, how do I know to do that? Just go ahead and do that automatically. Once I got to this point. Because I'm using the ideal gas law. Once I see I'm using the ideal gas law, I've got to make everything match that constant R. Like way up, I'm going to need kelvins and I'm going to need atmospheres. So let's just go ahead and do that. Okay, so our moles of O2 have our atmospheres. And let's see the volume. 57.2 milliliters. So we're going to have that in 0.0572 liters. And that's going to be over with 0.08206. By the end of this chapter, you should have that one memorized.
Where's the 0.05?
It's going to be, come on, go up there. Come on. You get, there we go. Now, there we go. See the 57.2 milliliters? Yep, we just got to change it to liters. Because again, liters is a unit in the constant R. And then, of course, we're going to need our 295 Kelvin. The number of moles of O2 should end up being about 2.22, 10 to the negative third moles of O2. All right, now we have moles of O2. Now, if I want a mass percentage, the first thing I'm going to need is the mass of the sodium chlorate, okay? Because it's set an impure sample. So that tells you sodium chlorate is in there with a bunch of other stuff. And I know it's really freaking hot in here, isn't it? So the sodium chlorate's in there with a bunch of other stuff. That's why it's asking for a mass percentage. Kind of, it's an idea of like, well, how much of this sample is actually sodium chlorate? So the first thing we're going to need is a mass of sodium chlorate. How do we get there? Right, we have moles of O2. That's why we started with the reaction equation. Come on, you can do it. There we go. That's why we started with the reaction equation. We can use the stoichiometry of the reaction equation to find moles of sodium chlorate. And then we can find the mass of sodium chlorate. I like to do it all as all in one shot. So I'm going to take sodium chlorate, add it up. It ends up being about 106.44 grams per mole. And now I'm going to say my moles of O2 from the reaction equation. I see I have 3 moles of O2 to 2 moles sodium chlorate. And then my sodium chlorate, 106.44 grams per mole. That means in this sample has 0.158 grams of sodium chlorate. Remember, there are no stupid questions unless that question is, may I lick a light socket? That one's a stupid question. I might let you do it because if you're going to ask, Darwinism has some place in our world. It's just stuff from years past. There's a reason when you read safety manuals, they have stuff in there. It's like, why would you need to tell me that? And someone did it. Now, we want a mass percentage. So we see how much sodium chlorate we have. Let's go back up to the problem and look. Anytime now. You can do it. There. What is the total mass of our sample? Yep. So that is the total mass. And only 0.158 grams of that is sodium chlorate. How do we find the percentage? You're making it too hard. We divide it. We take the grams of sodium chlorate. Our mass percent. That makes our mass percent about 18.03%. So yeah, like some of the experiments you do in lab, like you did one like this last semester with the yeast and the hydrogen peroxide, you can find out a lot. It kind of helps to know some of the theory before you do it, but you'll do a lot of stuff like this in labs as you go through your careers, you know. Like for example, like your gases. Where do you think you'd have to figure out percentage of a gas in a solution? Or maybe not even a gas, but percentage of a certain compound that was bubbled into a solution. Oxygen stats. So it is going to end up becoming important. Okay, so since this internet connection is dying and it's just about time, we'll go ahead and call it for today. We'll pick it up on Friday. Yeah.